Welcome to this video from Derby Physics Tuition, and I'm working with a student who is entering the physics aptitude test at the University of Oxford, and this is a question from the mechanics unit. And this is a great question. There's a lot of areas of physics from the mechanics unit that you need to have an understanding of. So this video really is applicable to all. It's a great question, as I said, that brings in a number of different areas of physics within mechanics. So let's have a look at the question, and quite a wordy one. So there are lots of different parts to this. We're going to go through it all, but a gun is designed that can launch a projectile of mass 10 kilograms at a speed of 200 meters per second. The gun is placed close to a straight horizontal railway line and aligned such that the projectile would land further down the line. A small rail car of mass 200 kilograms and travelling at a speed of 100 meters per second passes the gun just as it is fired. Assuming the gun and the car are at the same level, at what angle upwards must the projectile be fired in order that it lands in the rail car? Okay, so I like to draw a little diagram first of what we've got here. So we've got our rail car, and just draw the rail car in like that. Okay, and it tells us that the car is moving with a speed of 100 meters per second, and we've got a projectile that we want to launch and land into the car. So what angle must the projectile be fired? And we know that it's launched with a speed of 200 meters per second, and we want to know what angle, this angle here, that it should be launched at. So how are we going to figure that out? Well, what we need to ensure is that the horizontal component of the projectile is also 100 meters per second. So it has the same horizontal speed as the small rail car. So if we do a little bit of trigonometry here, here is our component, and we want it to have a horizontal component of 100 meters per second, and there is our angle that we want to work out. So a little bit of trigonometry. Let's draw our triangle. So that is 200, that is 100, and that is theta. Okay, and so we know the adjacent, we know the hypotenuse, so cosine of theta is the adjacent over the hypotenuse, which is 100 over 200, which is 0.5, and if we calculate theta, that gives us an angle of 60 degrees. So just to go through that again, we want the projectile to have the same horizontal component, same speed as the small rail car, and we know that the speed of the projectile is 200 meters per second, but we want its horizontal to be 100. So just by drawing a diagram like that, it really helps me to see what the situation is, and we've just used some trigonometry to work out that the angle is 60 degrees. And moving on to the next part of this question, how long does it take for the projectile to reach its maximum altitude, so its maximum height? And so we're going to use a Suvat equation here, and we're trying to work out the time. Now, at its maximum height, its vertical velocity will be 0, and the acceleration is the acceleration due to gravity, which is acting in the opposite direction. So we say that is -10, and we're not given, we don't know what the maximum height is, and so we need to work out the vertical component of the launch velocity. So how do we work that out? Well, we've got our projectile was launched at 200 meters per second, and we know from the previous question that the angle of launch from the horizontal was 60 degrees. Now we want to know the vertical component of that initial launch speed. So this angle here is 30 degrees. So the vertical component will be 200 sine 60, which is 200 times √3/2, and that is equal to 100 √3 meters per second. So we now know our vertical component of the launch velocity, which is 100 √3. So we can now use the Suvat equation. What are the Suvat equations to work out the time? And we've got V equals U plus AT. Let's put our numbers in. Our final velocity at the highest point is 0. The initial velocity is 100 √3, and the acceleration is 10. So just rearranging that, -10t equals -100 √3. So t will be equal to 10 √3 seconds. So that is our answer for that part. We've calculated the time for the projectile to reach its highest point. And moving on to the next part of the question, how far is the rail car from the gun when the projectile lands in it? So basically asking for the range of the projectile. Now we know that it takes 10 √3 seconds to reach its highest point, so it will take the same time to come back down. So the time that the projectile is in the air will be 10 √3, which if we work that out is 17.3 seconds. Now we've got to double it, because 17.3 is the time it takes to get to its highest point, and it will take the same time to come back down. So that will be 34.6 seconds. Okay, and now we can use if we just consider its horizontal motion, there are no forces acting horizontally. We're assuming that there is no air resistance, and so horizontally the acceleration is 0. So we can assume that it's traveling at a constant speed, that its horizontal component is 100. It doesn't change, and 100 is what we calculated from the first part of the question. So basically we can just use the equation speed equals distance over time, and rearranging that, distance equals speed times time, and v is the horizontal component, so it will be 100 times the total time it was in the air for, 34.6, which gives us a distance of 3,460 meters. So first three parts of this question are really good revision in terms of developing your understanding of projectile motion and the physics involved. And moving on to the next part, without considering energy, calculate the projectile's maximum altitude. So we've got to use CVAT again, considering the vertical motion of the projectile, and the vertical height is what we're trying to work out, S. The vertical component we calculated previously is 100 root 3. The vertical velocity at its highest point will be 0. G is acting in the opposite direction, so it has that is minus 10, and we calculated the time, but we don't need it in this case. So we're going to use another CVAT equation, v squared equals u squared plus 2as, and we know v, u and a, and so we can calculate s. So if we rearrange that first, we get that s equals v squared minus u squared over 2a. Okay, we will put our numbers in, so 0 squared minus 100 root 3 squared, all divided by minus 2 times 10, so we get minus 20 there for the denominator. Okay, and if we work that out, the numerator comes out as minus 30,000 divided by minus 20, which gives us an answer of 1,500 meters. Okay, and a nice bit of revision again for using the physics behind projectile motion and using CVAT equations. So the next part of the question is asking you to consider energy. Now consider energy. What is the initial kinetic energy of the rail car, and what is the initial kinetic energy of the projectile in both the vertical and horizontal direction? So for the rail car in red, it has a mass of 200 and it's moving at a speed of 100 meters per second, and kinetic energy is equal to half mv squared, which is a half times 200 times 100 squared, which gives you an answer of 1 times 10 to the 6 joules. And the kinetic energy of the projectile in the horizontal direction is half VH is the component of the speed in the horizontal direction, so that's half times the mass of the projectile times 100 squared, which is 5 times 10 to the 4 joules, and in the vertical direction times the mass again times, and the kinetic energy of the projectile in the vertical direction will be 1.5 times 10 to the 5 joules. So just to recap, have we covered everything? We've calculated the initial kinetic energy of the rail car, which is here, and the kinetic energy of the projectile in the vertical direction, which is that number there, and the kinetic energy of the projectile in the horizontal direction, which is that number there. And moving on to the next part, using your calculation of the projectile's initial kinetic energy, again calculate the projectile's maximum altitude. So this question keeps getting better and better really in terms of helping you to understand the physics involved that you've studied. So the kinetic energy that the projectile had in the vertical direction we calculated as 1.5 times 10 to the 5 joules, and the kinetic energy will be transferred to gravitational potential energy. So at its highest point, all of this energy will be transferred to gravitational potential energy. So we can say that 1.5 times 10 to the 5 equals mg times the change in height, which is what we're trying to calculate. And so if we rearrange that, let's just put our numbers in first. Mass of the projectile is 10, and if we calculate that, it gives us the same answer that we got before when we used the Suvat equations to calculate the maximum altitude. So you could either do this by, as you've seen in the question, using Suvat, or by considering the change in energy. They both give the same answer. Okay, so moving on to the last two parts of the question. When the projectile lands in the rail car, why does the velocity of the car not change? Okay, so how do we solve this one then? Well, we need to use the conservation of momentum. So we need to look at the momentum in the horizontal direction. So before the projectile lands in the car, if you remember, P equals mv, and the momentum of the projectile is mass times velocity, and its horizontal component is 100, and the momentum of the car is its mass times its velocity, which is 100, and adding those two together you get 21,000 kilogram meters per second. And so that is the total momentum in the horizontal direction before the collision. Now, what's the situation after? So this is when the projectile has landed in the car. So by the principle of conservation of momentum, before the projectile lands in the car, the momentum is 21,000, and the momentum must be the same after the collision. So we can say that P equals mv equals 21,000. That is the total momentum after the collision. And so we've got that 21,000 is equal to the total mass. Now the total mass of the projectile and the car is 210 kilograms, and if we work out the 21,000 over 210, which is 100. So the question is asked, why does the velocity of the car not change? Well, by considering the conservation of momentum, we've shown there that even though the projectile lands in the car and you've got an increased mass, the velocity in the horizontal direction does not change. So we've solved that, or we've answered that part of the question. And moving on to the final part of this question, assuming that the projectile remains in the car, what is the combined kinetic energy of the car plus projectile after the projectile has landed? To three significant figures. So kinetic energy equals half mv squared, and we've got a half times the combined mass, which is 210, mass of the car plus the projectile, times the speed squared, which is 100, which we got from over here, and that, if you calculate that, comes out as 1.05 times 10 to the 6 joules, to three significant figures as the question has asked for. So what a great question for revising a number of areas of mechanics. We've looked at energy, momentum, Suvat equations and projectile motion, all within one question. So it really is a good question for testing your understanding of how all this physics works together. And if you have any comments or any questions, please do leave them in the comments section below, and thank you very much.